floor is yours.
Thanks, and thanks for invitation. In this talk, I will give an algorithm that gets as an input an n-vertex graph G and an integer k, and outputs a tree decomposition of the graph G of width at most 2k plus 1, or determines that the tree width of G is larger than k. And the running time of this algorithm is single exponential in k and linear in n. Okay, so the plan of this talk, I first talk about something preliminaries and motivation, and then I give some background on some results that this builds upon and the outline of the algorithm, and then I'll try to give a quite detailed description of the algorithm, with first focusing on the main graph theoretical concepts of the algorithm without caring too much about the running time, and then discussing how to do this actually so that it's single exponential in k and linear in n. Okay, so let's define tree decomposition. So I think most people know this, but I'll just fix some definitions. So tree decomposition of a graph G is a tree T whose each node I is associated with back Bi, which is a subset of vertices of the graph, and this satisfies that the vertices of the graph are equal to the union of the backs, and for each edge there is some node of the tree decomposition such that the edge is a subset of the back of the node, and then for each vertex of the graph the induced subtree of the nodes whose back contains the vertex is connected. And the width of a tree decomposition is the maximum size of back minus 1, and the tree width of a graph G is the minimum width of a tree decomposition of G. Okay, so why we care about tree decompositions or tree width? So given a graph with a tree decomposition of width k, we can solve a lot of hard problems in time efficiently if k is low. So in time that is exponential only in k, and linear in n. So for example, maximum independent set, minimum dominating sets, ternary tree, etc., etc. So hundreds of problems are examples of this. And we should note that so these are dynamic programming algorithms that get the tree decomposition as an input. So to actually solve this in time single exponential k and linear in n, where k is the tree width of the graph, we need to be able to find a tree decomposition of width at most constant times the tree width of the graph in time single exponential k and linear in n. And just to motivate optimizing this approximation ratio C, so we can compute like if you have an approximation ratio of 5, then the dynamic programming for the dominating set, it takes time like 243 to k. While if we have approximation ratio 2, it takes time like only 9 to k. Okay, and then let's look what kind of FPT algorithms we actually have for computing tree width or approximating tree width. So basically, the best FPT algorithm for exact computing of tree width is the algorithm of Bodlaender from 96. So it's exact algorithm, and it's very good algorithm in that its time complexity is in fact linear in the size of the graph. But dependency on the tree width k for this algorithm is quite large, so it's exponential in the cube of k. And then if we ask for algorithms whose running time is polynomial, completely polynomial, we ask, can we obtain constant factor approximation? So no constant factor approximation algorithm that's polynomial time is known. So basically the best approximation ratio in polynomial time is square root of log k. But if we just want FPT algorithm, then we actually can achieve constant factor approximation, and single-exponential dependency on K. So the algorithm of Robertson-Seymour from graph minors, it achieves this, but with a quadratic dependency on n. There are actually quite a lot different algorithms for doing this. So FPT and exponential K with constant factor acquisition ratios for example, algorithm Treewidth, Lagergen, and Amir. And but none of these algorithms actually has both single exponential time in K and linear in n. But in 2013, Bodlaender, Draghi, Fomin, Loxton, and Bilitsuk gave algorithm that is for Treewidth that is 5 approximation algorithm and works in single exponential time in K and linear in n. So this is what we really want for solving problems in this kind of time. And they also gave a 3 approximation algorithm, but with n log n dependency on n. And so far, you can see that this 3 is the best approximation ratio that is better than this exact algorithm. And in this talk, what I give is 2 approximation algorithm that works in time single exponential in K and linear in n. So it improves upon both of the algorithms given by Bodlaender and others. And just to advertise this result a bit more, it actually happens also that this constant hidden by this O notation here. So in my algorithm, this is I think significantly smaller than in this algorithm. So what I can give a bound of 2 to 11K, and I think for this algorithm, it can be estimated like maybe at least this, but don't take this value too seriously. So it's just, I don't know how to optimize it like perfectly, but yeah. But I think like anyway, this is for my algorithm, this is smaller. Okay. And so next, I'll talk a bit about the background of this result and give some outline of the algorithm. Okay, there's nothing in chat. Yeah. Okay. So for this algorithm, we need as building block, we need to use this compression technique of Bodlaender. So which is used by like all linear time Treewidth algorithms currently. So we can set this technique like suppose there is some C approximation algorithm for Treewidth that needs a tree decomposition of with like OK as an input. Then there is a C approximation algorithm for Treewidth without needing any tree decomposition as an input. So basically, and this causes only polynomial overhead in K. So basically, we can in 2 approximation algorithms. So basically, we can assume a tree decomposition of with 4K plus 3 as an input. Was there something in chat? Okay, no. Yeah, this and then the more like natural way to state this new algorithm that I'm going to give is that the input of the algorithm is again n-vertex graph G, but this time it also has an input a tree decomposition of G of width W, and it outputs a tree decomposition of G of width at most W minus 1, or it decides that okay, W is already at most 2 times 3 plus 1, so the input tree decomposition is already 2 approximations. So it either improves the input tree decomposition, or decides it's already good. And the running time is single exponential W and linear n. But by this Bodlaender compression technique, we can assume that W is like 4K plus 3. Okay. And now another thing that I want to briefly talk about is the proof of Bellenbaum and Diestel, on which this algorithm is based on. So this proof, it talks about positions. So we say that tree decomposition is lean if for any two bags bi, bj, and vertex sets y and z that are subsets of these bags, we have that the number of disjoint paths between y and z is minimum of size of y, size of z, and the size of a minimum size bag in the path between y and z. So basically this is, if you have lean tree decomposition, then the number of disjoint paths in two vertex sets that are subsets of bags, it matches the trivial upper bound given by the tree decomposition. And what originally Thomas proved, and then Bellenbaum and Diestel gave a simpler proof, is that every graph of Treewidth K has a lean tree decomposition of width K. But what we are actually not interested in this theorem, but on the proof idea of Bellenbaum and Diestel. So basically, the proof is that they suppose they have a tree decomposition that is not lean. And then, so there is some example of sets y and z that are subsets of some bag for which this does not apply. And what they show, they can use this example to apply an improvement step to the tree decomposition. And they show that this improvement step, it doesn't increase the width of the tree decomposition, and it decreases some invariant on the tree decomposition. And crucially for us, it's that we can read the, so they do not care about algorithms, but if you read the proof, you can see that given this kind of lean witness YZ pair, which doesn't satisfy this, we can actually implement this improvement in polynomial time. Okay, and now what we can observe, it's not very hard to prove that if we have a bag bi of size more than 3 times Treewidth plus 3, then we can find this kind of lean witness YZ that is both y and z are subset of the bag. So we can use this improvement procedure of Bellenbaum and Diestel to improve the tree decomposition. So basically now we have a tree decomposition. We can always take the largest bag and try to find this lean witness, and if we find it, we can improve it, and if we don't find it, we can conclude that its Treewidth is larger than this. So basically a tree approximation algorithm with this kind of time complexity, so not quite linear in n, but single exponential k, it follows quite directly from the arguments of Bellenbaum and Diestel, with just some standard techniques applied. Okay, and to arrive to our two approximation algorithm, what we basically do is we do just some improvements to this thing of Bellenbaum and Diestel. So to get approximation ratio 2 instead of 3, we don't really use these lean witnesses, so you can forget everything I said about lean tree decompositions or lean witnesses, but we use like 3-way separations of bags. So this can be thought of like a 2-way separation of bag, but what we use is we use 3-way separation. So we generalize this to 3-way separations. And then to optimize the time complexity to be linear in n, we kind of make a local version of this improvement so that we don't have to edit the whole tree decomposition every time and do some invariant analysis. And what I think is really elegant here is we use, like, at the same time that we are improving the tree decomposition, we use dynamic programming on it to actually find these 3-way separations on it. Okay, so yeah, so this is like a rough outline of the algorithm. Are there any questions at this point before I go into more details? Okay, no questions. Okay, so now let's go to main concepts of the algorithm. So first, let's define a splittable back. So this is the back that we are applying the three-way separation on. So we say a back W of tree decomposition is splittable if the vertex set of the graph can be partitioned into C1, C2, C3, X, where X is a separator that separates each C1, C2, C3 from each other. So here's some picture with X being the green area. Yeah, so X separates these components, and what we require is we want this to satisfy size of this satisfy some inequality. So basically, the intersection of the back W that we are splitting with each component and union X should be smaller than the size of the back W for all of these I, for all of these C1, C2, C3. So basically, the intuition for this inequalities is like, if you think about a single back W here, now we can like locally improve this by instead of having this single back, we can put the separator X in the middle and then have three backs like W intersection C1 union X, W intersection C2 union X, W intersection C3 union X here. And know that this basically what this says is that each of these has smaller size than W. So this kind of improves the tree decomposition locally. So and then the hard thing is to argue that this applies to globally to the tree decomposition also. Okay. And before we go into doing this for the whole tree decomposition, let's prove simple lemma on back. So basically, we have a lemma says any back W of size at least 2 times Treewidth plus 3 is splittable. So this says that as long as we have a back that is larger than, as long as we have tree decomposition whose width is larger than 2k plus 1, we can take the largest back and say that it must be splittable. And basically, the proof how to prove this is very standard. So we can just let this separator X in this split C1, C2, C3 X to be like half balance separator of W of size Treewidth plus 1, which exists by just considering some optimal tree decomposition and picking the like center back. So it's very standard argument. Yeah. So I'm not saying more about this. So okay, and this is the only place in the algorithm where this approximation ratio 2 appears. So like yeah, it is not needed anywhere else. So from this point we just say that we have a splittable back. Okay. So now let's do the splitting more globally, the tree decomposition. So let's have the back W. So let's consider the back W as the root back of the tree decomposition. So I think it's simplest to think about it to take it as a root. And let's have some split of W. So we say always that this kind of partition of the vertex set is split if it's the thing that makes it splittable. And now for each I in 1, 2, 3, we obtain a tree decomposition Ti of the induced subgraph consisting of the component Ci union X by just taking this tree decomposition T, and for each back taking just the intersection of the back with this induced subgraph. So now, like clearly, if T is the tree decomposition of G, then if we take this tree decomposition and take the intersection of each back with the vertex set of this induced subgraph, we get the tree decomposition of this induced subgraph. And now what we want to do is we have these tree decompositions T1, T2, T3. We want to combine them with the separator X of the split in the middle. So like in this picture. And this is like almost tree decomposition of G. So basically, because this is tree decomposition of the, we have tree decomposition of each of the induced subgraphs. So it satisfies the conditions 1 and 2 of tree decompositions, but it doesn't satisfy the connectedness condition. So there might be some vertex xj here in X, so that the backs containing xj are not do not form a connected subtree of this tree decomposition. And now what we want to do is we want to fix this tree decomposition so that it satisfies this condition. And what is the magic of Bellenbaum and Diestel is basically saying that we can fix the tree decomposition without any cost. So let's see how we do it. So basically, we fix this connectedness condition by just inserting vertices xj that are in the separator to backs. So basically, maybe if you think about it, if we want to just, we don't want to alter tree decomposition in any other way, but just inserting vertices, then there's like a unique minimal way to fix it. So we say that each back is instead of just this, we add some bx, which is subset of the x to it to fix this. So let's see this by example. So let's have some split of the root back w. So here is t, here's the root back w, and let's have some split of the root back. And now what we do, we insert both like x1 and x2 to this root back, and then let's consider the path from the back here containing x1 that is closest to the root, and we insert x1 to each back in the path, and same for x2. So we have here the region containing x2, and we insert x2 to each back in the path from here to root. So to have some terminology, we say that like the home back of this vertex x1 is the back closest to the root that contains x1. So here it's C, and the home back of x2 is D, it's here. And what we do is we just insert x1 to each back in path from the home back to the root, and same for x2. And next let's try to bound this to show that this tree decomposition is not worse than what we start with. But are there any questions at this point? So I think like now understanding this construction is like quite crucial for the rest of this talk. Okay, no questions. Then let's go forward. Now that we have that this back BI has this definition, so it's the intersection and the additional fixing vertices. Now we have that our construction actually yields a tree decomposition of G, and which looks like this. So the root backs W2, W3 are connected to the separator back X. And now what we have like directly from the definition of split, like we already discussed, all of these vertices, all of these backs, I mean, shown here, so W1, W2, W3, X have size smaller than the original back W that we are splitting. So it seems we are improving the tree decomposition, at least here, like locally around this root. And what remains is to show that also for all other backs, this construction also improves the tree decomposition, or at least like decreases some invariant or something. It doesn't make it worse. Okay. And so to do that, we need to have some extra properties for the split. So let's have some split of a back W. We say it's a minimum split if among all splits of the back W, primarily it minimizes the size of the separator X, and secondarily minimizes something else. But let's just use this primarily condition to prove something. Okay. So now let's have a minimum split. So a split that minimizes the size of X. Now we prove for all backs B and distinct ij, it holds that this set of fixing vertices Bx is smaller than the intersection of B with C1 union Cj. So basically what this means is that more goes out from a back that goes in. So basically this Bx are things that go in and this is what goes out. So this is when we do this construction, this back Bi has size at most the size of the original back B. So and how to prove this lemma is basically, okay, let's suppose the contrary. So let's suppose this fixing vertices have size larger than this intersection. Now let's construct a better split. So let's take X prime, we remove this Bx, this fixing vertices from X, and insert the intersection with C2, C3. And so now, like clearly, okay, by definition, we have this X prime is smaller than X. So if we get the split where this X prime is separator, this contradicts the minimality. And basically, to argue why we actually get a split by doing this is by this picture here. So now here it's like we have this green area of W, orange area of B, and sorry, blue area of W, orange area of B, and green area of X. And basically the Bx vertices, how we define them is that they are like below B in the tree decomposition. Like all backs containing vertices of Bx are like below back B. So Bx is like things below B here. And now when we do this, basically what happens is we take this out from below B, but we insert things to B so that like this component C2 doesn't have any more access to below B, and neither does C3. So basically, I think maybe this picture is the best way to briefly argue why this works. So why we get a new split by doing this. Okay. Are there questions about this proof? Okay. No questions, so let's go forward. And now we wanted also some secondary condition to say that the back, so to say that the split of a back is a minimum split. So what we want it secondarily minimizes some distance function, some sum of a distance from xj to w. So how this distance is defined? We defined it as a distance from the home back to the root back in the tree decomposition. So basically for x1, so let's again have a split where we have a separator x1, x2. So basically if you have like x1 here, the home back is c, so the distance to the root is 1, 2, 3. And for x2, the home back is d here, so we have distance to root, which is 2. So for this split, we have this distance function is a sum of them, so it's 5. And so yeah, so we want the separator x in the split primarily minimizes the size of x and secondarily minimizes this distance function. And why we want this is that now we can prove a stronger bound to bound the number of these fixing vertices that we need. So now what we can prove is that if we have a minimum split, then for all backs B, for which this set of fixing vertices is empty, we can prove that this set of fixing vertices is strictly smaller than the set of vertices that goes out from the back. So basically for distinct ij, the intersection of the back union CIJ. So basically this is the same as the previous lemma, but this says that the inequality is strict if we have this Bx fixing vertices is non-empty. And basically it also says that this is strict if we have this non-empty. So this implies the resulting back Bi is strictly smaller than the original back B if Bx is non-empty. And how to prove this? So this proof is exactly same as before. So now if you think about it, if we have this Bx is equal to this intersection of C2, C3, B, then what happens is that we don't change the size of the separator, but we move the separator like up in the tree decomposition. And so we move vertices from below B to B in the tree decomposition, which strictly decreases this distance function. So yeah. Okay, and now to summarize this, if we use minimum splits, then what we have is that we have the resulting back Bi has size at most the size of the orthogonal back B for all backs B, and if Bx, if the set of fixing vertices is non-empty, then we have that it is strictly smaller than the original back B, and which implies also that it is strictly smaller if this original back intersects more than one of the components C1, C2, C3. Okay, and now if you look at this, like the only case when we can have that some resulting back from this construction has the same size as the original back, and it is not smaller, is that this fixing vertices is empty and the intersection of the back with the other two components is empty. And like in this case, what we have this is actually like, if we have B1 is this large part, then we have like B2 and B3 are small. They are like subsets. They must be like subsets of the separator X. And so most importantly, what we have like if the original back B has size W, then at most one of these has size W. And now what we get is if we split the largest back W of a tree decomposition T, we do not increase the width of T, and we decrease the number of backs of the largest size. So doing this splitting, like n times will for sure decrease the width of a tree decomposition because we start with at most n backs of size W. And so now, like, if you think about it, it's quite straightforward, like using standard techniques like, I don't know, dynamic programming or important separators to implement finding the splits, like finding a single split in time that is single exponential in the width and linear n. So like in total, just with standard techniques, we get algorithm that is single exponential in k and quadratic in n, and achieves two approximation. Okay. And yeah, so next we are going to optimization of this algorithm. But now, are there any questions at this point? Okay. Yeah, I guess no. So let's go forward. So let's go into optimizing this dependency on n from quadratic to linear. So the first issue we have with this algorithm is that we might need to split the tree decomposition n times just to increase the width by 1. So by implementing the splits, like we described, like editing the whole tree decomposition, just only the back editing process will take like at least quadratic time over the course of the algorithm. And how we solve this issue is that we modify this back editing process. So we define what is editable back, and basically what we show is we show how to implement the splitting operation so that it takes time that is like polynomial in the width of the tree decomposition and linear in t, where t is the number of editable backs of the split. And then now what's important is that we prove that this number of editable backs in the splits it respects some invariant. So basically so that if t is the original tree decomposition and t prime is the tree decomposition that we get by the splitting operation, then we have this number of editable backs is at most a difference. And where this potential function is like this, so it's sum over all backs of the tree decomposition of the 7 to the size of the back. So this means that the time taken by this back editing, so it's bounded by this original value of this potential function, which is like at most single exponential in w times n. Okay, and here like the base of the exponent is 7, but it can be optimized to 3 by adding some polynomial terms. But 7 is something simple. Yeah. And okay, so let's go into more details how this is done. So let's define editable back. So let's have again a split of a root back w of a tree decomposition, and we said back b is editable if it intersects at least 2 of the components and its parent is editable. So now the parent is of course with respect to the root w. So let's look at this example. So we have some split of this root back, so this root is always editable, okay, and then this back a here, it's editable because it intersects c1 and c2, and its parent is editable. But this back b here, it's not editable because it intersects only the component c1. Yeah. And then this back C, okay, this intersects both components C1 and C3, but its parent is not editable, so we define it to also be not editable. And then, okay, here D is editable, and again, E is not editable, so yeah. And okay. Okay, now what we do is after defining the editable backs, we change this split somewhat. So okay, so now let's look at some non-editable back B here. So this is non-editable, but whose parent A is editable. Okay, so it's like I don't know, minimal non-editable back. So now in this subtree below this back B, what we do if we have vertices like this back intersects only the component C1. But now if in this subtree we have some back that also intersects like component C3, what we do is we also assign T's to C1. So in particular here we assign H from C3 to C1, and in the split. And it's like it should be quite clear that we can do it. Like basically, the only way from here to go to the root back is to go like through the separator X or through C1. So why not we assign this also to C1? And like this, and how this assignment is actually done is we do it like implicitly, like when we have some separation and we are like exploring the editable bags, then if you know, okay, this is non-editable, then we just implicitly assume that, okay, everything below this is like this intersects only C1, so everything below this also intersects only C1. Okay, and now after this like reassignment, we can say that a bag is editable if and only if it intersects at least 2 of the components of the split. And also, of course, because of this parent condition, we note that the editable bags, they form a connected subtree that contains the root. So in particular, we can like explore the editable bags fast in the tree decomposition. Okay, and now we can observe like if we have a non-editable bag and we have minimum split, then this fixing set is empty always. And then if we have like a minimum split, if we have bag B that is not editable and intersects only the component C1, like in previous slide, then we have like this B1 of the resulting bags is equal to the B, and this B2 and B3 are subsets of the separator X. And because of this reassignment, this holds for all bags in the subtree below this. So basically, what we do now is we basically for non-editable bags, we have that in this construction, we have like only one representation of them. And other versions, like here we have the real version is this B1, and the other versions are just subsets of X, and they're subsets of X like everywhere in the subtree. So and like if you have a subtree with all bags are just subset of the separator X, then for sure we can drop the subtree because we anyway have a bag X here in this construction. So what happens actually in this now like local construction is like here, if we have this editable bags here, then for editable bags we do this construction. So we triple take them into three parts and merge by the separator X. But for this non-editable subtrees, we don't touch them. We just do this this thing and then reattach the non-editable subtrees to this construction appropriately. Yeah, so for example, if this B intersects only C1, then for sure it should be attached to AA1. And same if this E intersects only like the component C2, then it for sure should be attached to this D2. And now we can do this splitting just by removing the T editable bags. So we said T is the number of editable bags, and inserting like 3T plus 1 new bags in place of them and connecting these subtrees, non-editable subtrees accordingly. And basically detail in this is that to do this actually efficiently, we have to maintain that our tree decomposition has maximum degree 3. And this is not hard to do because we can just like the only place where we can get degree increase is like for this root. So we can just every time we split, we do like a duplication of each of these like W1, W2, W3. So this increases the number of new bags inserted to 3T plus 4. Okay. Yeah. And now, if we have now we can reconsider this potential function, like what happens to it when we do this. So it's this kind of sum of 7 to the size of bag, and because for editable bags we have that this resulting bag Bi is always smaller than B, because they intersect multiple components. Then we can do some computations with this, so that okay, the difference between these this potential function is bounded by the number of editable bags. And So our algorithm, we can implement it so that we edit at most a number of backs to this single exponential in the width and linear n over the course of the whole algorithm by this potential function. Okay, and then there is this second issue is that we need to split every back, so we maybe need to perform a linear number of splitting operation to decrease the width. So we need to find each split in amortized time. It's like single exponential in the width, and doesn't depend on n. And basically, how to do this is we use dynamic programming on the tree decomposition simultaneously when we edit it. So basically, if you think about it, so the splitting is like computing, like determining if we have some split of a back. It can be done by very simple, like standard dynamic programming on tree decomposition, and also like optimizing the distance is done so that basically for getting a minimum split, the distance optimization is also very nice to just put in this dynamic programming. So basically, we can do this dynamic programming like initially in this kind of time, like linear n. But then what we should note, if we have computed the dynamic programming table on this tree decomposition for all backs, then we can reroute this dynamic programming to an adjacent node by just touching like two backs only, like the root and the back next to the root. So we can move the root to an adjacent node in this kind of time. And basically what we do is we do like a DFS style editing procedure with the dynamic programming based data structure to do everything in this kind of time. And yeah. And so like for more details, here are some details to it. Like basically we maintain a tree decomposition T of maximum degree 3 and with at most W with that is rooted at some node R. And so basically, so we initialize it. We compute all the dynamic programming for all the backs, and then we can do this moving from another back by just recomputing the dynamic programming for two backs. So we can move the root to a neighboring node in this time, and then for determining, okay, we are at some we are like let W be the back of the root node, so we can determine if looking at the dynamic programming table at the root. Okay, and basically also like here is the issue that we need to actually determine the split, but what we need to do is we need to just like, if you find that okay it's splittable, what we need to do, we need to just explore the editable subtree to get like all useful information of the split. So we need to do like some backwards dynamic programming in here, but yeah, it can be done like and then there's like, you can say there's like a state operation which gets the internal state like the result of the backwards dynamic programming. So we can query like the like if we do the splitting operation, then we set like the internal state to some minimum split of the back that we consider, and then after that we can use this state operation to find out like what does this split look like in editable backs, and then we have like this editing thing that we just take the subtree away, and it's crucial that okay, the subtree that we take away is always be like the pointer or root is always in the subtree, and then we add some new subtree instead of it, and it's like, of course, it's like this kind of time complexity we can do it. Okay. And yeah, here are some details of this dynamic programming, but I don't know if it's really useful to go through this. So because it's very standard stuff. So basically, the dynamic programming state of at node I is just like for each split restricted to the back I, or basically, or this each split of the induced subgraph like below the back I. So we save this partition and this size h of the separator x, and then we like optimize. So we need to store the minimum value of this distance thing that we secondarily optimize, and yeah, and basically, of course, because we have a tree decomposition of degree 3, we can always compute this the dynamic programming state of a single back in this time, like based on the states of its children. And basically, like here's some picture which says from which you can note that okay, we have dynamic programming rooted at node R, and then if we change it to the node S, we don't need to update any other tables than the tables of R and S in this dynamic programming. Okay, so basically putting everything together, we just DFS over the tree decomposition with this move operations, and every time we see a back of size w plus 1, where w is the width, we apply the splitting operation and edit the editable backs like around it. And here it's like maybe it needs some argument to say that okay, this DFS actually this editing the tree decomposition doesn't mess up this DFS, but it's quite easy to see, and then we argue by the potential function that the number of nodes that we consider in this whole thing will be single exponential in W and linear n, and like each operation basically in this tree decomposition takes this time of time, and by the potential function it amortizes like this to total time complexity single exponential in the width, or single exponential in k, where k is our parameter, linear in n. Okay, so to conclude, so we gave two to OK, so single exponential time in k and linear in n time two approximation algorithm for Treewidth. And maybe just I don't yet have too much to say about what future directions there could be, but one maybe possible idea to look at this is basically this. We have this approximation ratio 2. It appears only in the lemma that guarantees that every back of this size is splittable. So, but what about can we do better analysis about what happens if we just continue splitting everything until we cannot split anything? Like what does the tree decomposition look at this point? And can we like maybe for like special graph classes can we get better bounds for the approximation ratio? I don't know. And also like for this purpose, the back splitting, like we had like 3 components, C1, C3, C2, C3, but basically it can generalize to any number of components you ever need. Okay. Okay, thanks. That was everything.
Thank you very much. Okay. So time for questions.
Okay.
Yeah. Well, doesn't look that any, right? So how this, yeah. Okay, then thank you once again. Yeah.
Yeah, thanks for the invitation.
Bye.